Hi, so this is a short description of certain concepts of signal processing. And to understand signal processing, first we have to understand what is a signal. So a signal are certain physical quantities in nature and their time behavior or temporal behavior of those physical quantities. That's what we model with signals. So basically when we say signal, we assume certain thing like xt. So what is xt? Now xt models some temporal behavior of certain physical quantities in nature, like variation of temperature with respect to time and something like that. So in signal processing, we deal with signals like xt or yt. Now these signals can have different values. Now these signals are broadly classified as a continuous time signal or a discrete time signal. So the signals whose support is infinite time, it's continuous time signal, and these continuous time signal are expressed as xt, while the discrete time signal are finite support, and finite support signal is expressed something like x capital N. So in general, in principle, in nature, we say that we deal with continuous time signals, but in computer, when we process those signals, we have to process with discrete time representation of those signals. So how do you understand the discrete time representation? By observing the continuous time signals at discrete time instance. So basically, we say that xn is when we observe the signal xt in certain time instance nt. So is the discrete time representation of the signal. Now the basics are clear, and then this signal can be a set of values. Now this xn can be a set of values at certain time instance. So this can be any set of values like 5, 2.5, 3, 4, whatever at certain time instance 0, 1, 2, 3 up to n minus 1. So it can be an n-dimensional set of values. Now this can be represented as a vector. So this x is a vector. And then we have to use some mathematical tools in signal processing fundamentally. These mathematical tools for the vector is something that I will discuss upon next. So what are the mathematical tools that we want to use? That is inner product of vectors. So between two things, the inner product is defined as x and y. Mathematically, the inner product is x dot y cos theta, where x and y have an angle between them, and theta is the distance, angular distance between them. So the inner product is basically the vector dot product. So if x vector is composed of x1, x2, x3 for an example, and y is composed of y1, y2, y3, the inner product between x and y should be x1, y1 plus x2, y2 plus x3, y3. Also in vector terms, the inner product can be expressed as xy is equal to x transpose of y in vector terms. So this idea of inner products is something that we use a lot in signal processing. So what are the properties of the inner product? So we have an n-dimensional vector x, which is defined as xn for n is equal to 0 to n minus 1. And we want to expand these n-dimensional vectors over a support of basis vectors uk in the n dimensions for k is equal to 0 to 1. And how do we expand these vectors? We can expand these vectors with some expansion coefficient xk multiplied with this uk and taking a running sum over k is equal to 0 to n minus 1. So we can approximate x as this. So this is the basis expansion of the vector based on inner product. And how xk is given? Xk is the inner product between these basis vectors uk and the signal x, normalized by the magnitude of uk. So this is xk. Now suppose we want to approximate this x in a lower dimensional space, which is a subspace of the entire n dimensions. So what is our lower dimension space? So we want to approximate it in a subdimensional space, that is k is equal to 0 to k minus 1, where k is definitely less than n. So this subdimensional approximation of xk, uk is giving us an approximated x marked with the tilde. So this approximate x is this. Here we say this approximation is equal to this only when they have a zero error. So the error of approximation E can be x minus of x tilde. Now then we move forward to the projection theorem, and the projection theorem is this. That after the first point of the projection theorem is that the error of approximation is orthogonal to the approximation itself, right? Now here we have to discuss, to do this we have to discuss some properties of the inner product. So what are the properties of inner product? There is one property of the inner product, that is the orthogonality property. So what is orthogonality? The orthogonality says that if two are orthogonal to each other, their inner product must be 0. So first part of the projection theorem says the error is orthogonal to x tilde. That means we have to prove that the inner product between E and x tilde is 0 using the property of the orthogonality. And the second part of the projection theorem says that if we take a projection space P such that it is equal to Z, given that Z is expanded over Zk times Uk in a subdimensional space k is equal to 0 to k minus 1, where k is less than the actual dimensionality n. So we say that the projection space is spanned by a set Uk, a basis set Uk, where k is varying from 0 to k minus 1 instead of n minus 1. In that subdimensional space, these are the z's. Then the second theorem of the projection theorem says that the difference x minus x tilde should be less than x minus z for all such z. And geometrically, the projection theorem leads to this idea. Suppose we have a three-dimensional space where we realize the vector x. Now we want to project it on a subdimensional space. So as we say that the error is orthogonal to x tilde, the best approximation of x is an orthogonal projection on the subdimensional space spanned by u1 and u2, and this is x tilde. This bases on the idea that the inner product between E and x tilde is 0. So how do we prove that? So we say that x minus x tilde and x tilde inner product should be 0. That means this inner product, where this we define x tilde, that is x tilde is xk times uk summation x minus x tilde, and this inner product, by inner product property, is summation xk common uk inner product of x minus x tilde, and the inner product is distributive, so it's summation xk uk comma x inner product minus uk comma x tilde inner product. Now x is expanded on the basis of uk, x tilde is also expanded on the basis of uk only. So these are practically the same and they cancel out each other and we ultimately get 0. That defines the orthogonality property, which means the projection of x on a subdimensional space is the best approximation and this is the projection theorem. The orthogonal projection of x on a subdimensional space spanned by a subset of uk is the best approximation of x. And then we come to the other property, that is the completeness property, that if we calculate the energy of this error, the energy of this error is x minus x tilde square integration, and if it is defined over a particular interval, whatever the interval is, minus infinity to plus infinity, and dt in continuous domain, this energy should be going to 0 if we limit on k tends to infinity. That means if it is defined over the interval on a, k, so yeah, so should be k is equal to something like this. The energy should go to 0, and that is the completeness property.